Okay, so what does K represent again?
Coulomb's constant.
Yeah, it's known as the Coulomb's constant or electrostatic constant. Okay, one thing that I want you to know, and this is an important distinction which is going to come up time and time again, is the representation of the electrostatic constant. Okay, goof that up. All right, so K that we're looking at there. K can also be expressed in terms of a different constant. This is known as the space permittivity constant. Space permittivity constant is going to be a very small number. It's 10 to the minus 12. All right, so the question is, what does that represent? So K represents the strength of the electrostatic force when expressed in terms of epsilon. What does epsilon represent? Any ideas? Or those of you guys who are electrical engineering majors, if you've taken in a sort of a circuits course or whatnot, what does epsilon represent? Does anybody know?
Maybe the distance.
Okay, so the distinction of this is going to become important later on. It's known as space permittivity constant. So number one is related to space, and so it's a constant related to space. So what does permittivity mean? So we have to focus on the meaning of it. So what do you think permittivity represent? I mean,
How likely it is to stay where it is.
How likely it is to stay where it is. Okay,
Yeah.
I'm gonna give you 5 points for at least trying to figure that out, guys. In a strange sort of way, space permittivity constant is going to set a limit to how fast this force can travel in space. Do you get that? All right, so space is gonna kind of put the brakes on in terms of how fast this force can get transmitted in space. That's what it means. All right, so which means that the force is gonna have a speed limit. It's not gonna go from point A to point B instantaneously. That's what it means. So the space is gonna actually resist the motion or speed of this force. All right, so now that we talked about it, all right, so the formulas look the same. There's a little bit of plagiarism going on the part of Coulomb. It could be that the British and French didn't like each other that much. You can't get away with that sort of stuff. So what gives it away is the fact that both of them are inverse square laws. You cannot come up with an inverse square law just conceptually. That requires a mathematical justification behind it. Gravity is attractive. Electrostatic force can be repulsive as well as attractive. Electrostatic force is going to be much, much stronger than the gravitational force. So those are the major differences. Okay, it's 8:30, so take a break for 10. Be back within 10. Okay, guys, this is one of my favorite problems. Let's talk about the hydrogen atom. We're going to be talking about the hydrogen atom forever. Those of you guys who will take modern physics, you can actually see the evolution of physics through the hydrogen atom from classical physics into modern physics. All right, the first model of the hydrogen atom is known as the semi-classical model. That's the one that we use in chemistry usually, as well as electrical engineering. It's otherwise known as the planetary model. Notice that you have the proton, the positive charge at the center, the negative charge moves about it, kind of like the way the planets move about the sun. Niels Bohr is the guy who came up with it, worked on it for 2 years between 1911 and 1913 and published it in 1913. He won the Nobel Prize for it in 1922, and this is how the modern quantum theory actually got started. This is the first model of the hydrogen atom, or otherwise known as the semi-classical model, because it's called semi-classical because it uses the concepts from classical physics. This is not the model of the atom that we use in physics today. All right. So the only question that I'm going to have is, how fast does the electron need to be moving about the nucleus so it's not collapsing into the nucleus? All right. So this is the problem number 1 from the handout. All right. So just go to Canvas and look at the problems. This is problem number 2 from Canvas. Otherwise known as the hydrogen atom problem. So we got the hydrogen atom. I'll set up the problem for you, and then we'll solve it. I don't want to spend more than 5 minutes working on it. All right, so here's the semi-classical model. You have the positive charge at the center, and moving about the center, you have the electron. It's going to be moving at a given speed. The electron is going to be located from the nucleus, a certain radial distance. And we got a bunch of numbers that we will get to use. All right, let's use this. This is E. Electron is going to be a unit charge. It's going to be negative E. Make this Q1. This is going to be Q2. All right, so radius of the hydrogen atom is an experimental number. It's an observation. It's 5 points. I'm thinking that's going to be 5 point something, but let's go back and double check. It's 5.29 times 10 to the minus 11. Okay, 5.29 times 10 to the minus 11. Okay, so I'm going to change that a little bit. I'm going to make it a little bit more exact. It's going to be 5.298 times 10 to the minus 10 meters. 5.29, 5.3, or is it 26? I don't remember. The only thing I'm going to say, the reason why this is important is because 10 to the minus 10 meters, that term that we're looking at is known as angstrom. Okay, so it's a unit that we use in modern physics as well as in atomic physics. So the size of the hydrogen atom is half an angstrom. Okay, so we got two charges, Q1 and Q2. These are unit charges. We'll get to use 1.602 times 10 to the minus 19 Coulomb for that. We may need the mass of the electron, which is going to be 9.11 times 10 to the minus 31 kilograms. Okay, so the only thing I'm interested in is the speed of this charge. How fast is the electron moving inside the hydrogen atom? Maybe express it in terms of miles per hour. And just for the hell of it, also let's express it in terms of the light speed. Okay, so we got the radius, we got the unit charges, we got the mass of an electron. And let's figure out the speed of this. All right, now the solution. Okay, guys, how do you solve a problem like this? I need some suggestions. What do we do?
Have a starting equation.
Okay, what equation are you starting with?
I would assume probably the electrostatic force equation.
Okay, how do you use the electrostatic force equation?
Force is equal to K times charge 1 times charge 2 divided by the radius between them squared.
Okay, my question is, why do you have to use the electrostatic force equation? I want to figure out the speed, guys. So how do you find the speed? What is it that you have to do?
Well,
What?
by using the force, can you translate force into an equation that equals that you can solve for velocity?
What equation would that be?
Centripetal force?
Yeah, centripetal force.
Okay, very good. I'm gonna give both of you guys 5 points. Guys, look at the motion. What kind of motion is this? It's circular motion, right? If it's circular motion, you have a generic expression for circular motion. Generic expression goes like this, which means that there's gonna be a force which is gonna be directed towards the center. You got the centripetal force. Okay, so what do we know? We know that it's circular motion, which means that there's gonna be centripetal force. And we know what the centripetal force is in this case. All right, so the centripetal force in this case is gonna be the electrostatic force. All right, so the electrostatic force is the force which is directed towards the center. So immediately you know how to do this. Okay, here's a generic expression for the centripetal force. And here's the expression for the electrostatic force. So you have Q1 times Q2 divided by the square of the distance. Okay, those of you guys who did not notice it, or you did, I don't know. There's something wrong here. What's wrong? All right, there's no square there. Okay, so we're done with that. All right, so centripetal force is the same as the electrostatic force. So the electrostatic force is the centripetal force. So they will be equal to each other. All right, so K, Q1 times Q2 divided by R squared is going to be MV squared divided by R. Solve for V. Like terms will cancel. All right, so one of the R's will cancel. And then solve for V. All right, so when you solve for V, what do you get? You have K, Q1 times Q2 divided by, it's going to be M, R. And then take the square root. All right, so Q1 is a net charge. This one is the positive one. Q2 is a unit charge. This is a negative unit charge. And then you got the electrostatic force constant, and you have E, and then you have negative E. You have the mass of the electron. You got the radius of the hydrogen atom, and then take the square root. All right, so K is our electrostatic force constant. It's going to be in terms of newtons meters squared per coulomb squared. Okay, so I got my numbers. So the only thing we have to do is just plug everything into this formula, and then we're done. Okay, so that's it.
Isn't that going to give us a negative number under the radical?
Okay, who said that? Okay, so Ian, you're saying it's going to give you a negative number under the radical. Absolutely, it's going to give you a negative number under the radical. So do we have a problem with that?
Sometimes.
I mean, in this case, definitely, right? Okay, so what's the problem with that?
Isn't there supposed to be absolute value marks around the charges?
No, I don't want to go there yet. What's wrong with what we have right now? Well, what's wrong with what we have right now is exactly what Ian was talking about. Do you want to have a negative inside a radical? Yes or no?
No.
No, not at this level. This is freshman physics, guys. You don't want to make it so complicated. You get a negative inside a radical, so what does it mean? Which means that you're done. There's nothing you could do with this. So how do you get rid of the negative? What is it that you have to do? I mean, I love the equation. I want to keep it. I don't want to give up at this one. It's too early to give up. All right, so how do we make it work if you have a negative? And then you go, wait a minute, I may be able to make it work. So how do you make it work? Why not just get rid of the negative? How do you get rid of the negative? What is it that you have to do? Okay, so here's what you need to do. Negative does not work. This equation, which is this one. Oh, I love this. It's modern art. I'm not going to change it. Gives you the force. It just gives you the value of the force, guys. This is not a vector. It's just a scalar. Do you get it? It tells you about the magnitude of the force, which means that the plus and minus signs don't matter. So what that means is you kind of have to get rid of the negatives. So how do you get rid of the negatives? You get rid of the negatives by taking the absolute value of the charges. So every time you see a formula like that, this formula is going to give you the magnitude of it. It doesn't give you the direction. So when you see signs, positive or negative, just get rid of them. So which means that you have to take the absolute value of these. As soon as you take the absolute value of those, the problem's solved. Okay, so all of a sudden we got an equation that looks like this. Okay, guys, plug the numbers in and check to see what you got. All right, so give me the answer in terms of meters per second.
2.19 times 10 to the 6.
2.1?
2.19 times 10 to the 6.
10 to the 6 meters per second. So that's 2 million meters per second, right? Okay, let's do a quick conversion. Give yourself 2 points for that one. Okay, so let's do a quick conversion to miles per hour, just to give you an idea. So meters per second to miles per hour. 1 meter per second is the same as 2.24 miles per hour. Like units will cancel. Okay, so what does this give you?
I got like four. I got really large number. I got like 4,905,600.
Okay, so roughly about 5 million miles per hour, right?
Yeah.
Okay, so also I want someone to express this in terms of C. What is C? What is C, my man?
Like
Okay,
the speed of light?
It represents speed of light. Okay, so convert this to the speed of light real fast. What is this in terms of the light speed? So you go from meters per second to C. 1 C is 300 million meters per second, right? So how fast is this? Roughly.
.0073.
So it's less than 1% of the light speed, right? Okay, cool. 0.0073. All right, so the number that I'm going to focus on is this one. So how fast is the electron moving while orbiting the hydrogen atom? Guys, it's like 5 million miles per hour. It's way faster than a Ford Tempo. 5 million miles per hour. That's how fast.